Welcome to Smarter Circuits. I'm your host, Ian Klein. This is an electromagnetic relay. So is this. And this. Invented in 1835 by Joseph Henry as a simple demonstrative device designed to illustrate electromagnetic properties, the relay has become one of the most important components in modern electronics. Automotive engineers use them to control heavy current DC circuits with smaller and safer ones. Heating and cooling manufacturers use them in control boards and thermostats for timing and cycling. Machine manufacturers use them to control powerful devices with computers without risking the computer circuitry. Now, in older thermostats and indeed some older automotive relays, the switch was operated by a thermomechanical device rather than electromagnetic, but this is rarely seen in modern devices. Relays themselves are pretty simple. A quick overview of how an electromagnetic relay works. Here I have a common relay with the cover off. You can see that there is a coil with a metal pin in the center. The pin moves an armature that is tensioned by a spring above the pivot. At the end of the armature are these contact leads which allow current through this set of pins or this set of pins depending on the powered state of the coil. When you apply power to the relay's coil, the electromagnetic field produced moves the plunger. The contacts on the outside are broken and the contacts on the inside are closed. This allows for isolated control of circuits by other circuits. This isn't the only way to achieve this, of course. In fact, most of the relays in front of me are protected by another device called an optical isolator. But we're just talking about the relays for this video. These aren't too far removed from the devices used to make the first logical processors. Relay logic computers were around before even the tube-driven ABC and ENIAC machines. While the tube and eventually the transistor and even later the integrated circuit would replace the relay for computing, the relay is still the best option for many other, often complementary applications. There's a really good reason for this. Because it takes very little force to move the contact arm of a switch, relays can be made to control dirty high current loads with lower power, often more sensitive devices. Many of these applications are beginning to spill over from the industrial and commercial worlds into the residential space. One such example is this Shelly relay, which I'll likely mention in every video I possibly can. The company that makes these, Allturco Robotics, was already making industrial machine controls and at some point realized that many of the same solutions used in these machines could be applied to home automation at very low cost. Now, I'm not sure who started using industrial components and technologies for home automation first, but Shelly products certainly do a pretty good job of taking IIoT technology, that's Industrial Internet of Things, and applying it to home automation. Another example of this crossover is the use of MQTT, or Message Queuing Telemetry Transport. Originally developed for the oil industry by Arlen Nipper and IBM's Andy Stanford Clark in the mid-90s, MQTT is the perfect way to integrate inexpensive and sometimes underpowered Wi-Fi devices in almost any automation project. I covered MQTT a bit in episode 2, so I won't go into too much detail there, but I will say that one unique feature is that MQTT is designed around devices that aren't always the most reliable communicators. One thing I'd like people to focus on, besides just how useful these devices are, is just how much you don't need much more than what we have here, which is just a power supply, a relay, and a button. In place of the button, we want to have some intelligent device that enables us to programmatically control the circuit. This is where it gets a little gray, and we have to weigh a lot of key factors. While a lot of Apple, Google, Amazon, Sonoff, and other companies' products offer some pretty novel features, they also come with risks and, more often than not, compromises in design or reliability. Take, for example, this smart plug. It requires a third-party cloud application to connect and manage the device. If the device loses internet, the only control you have is via this push button on the side, which is more than many of these devices offer. This is the inconvenient side of this plug. Now there's also a dangerous aspect to this particular device. When the mobile application used to set this device up first connects, it uses an unsecured ad hoc Wi-Fi network. When you send the credentials for your home network to this device, it is sent in plain text over a non-secure HTTP connection that can easily be sniffed. There is a very small window of opportunity for this attack, to be fair, but that's not the only vulnerability present. There's no limit beyond the hardware's maximum processing speed for turning the relay on and off, and there's no overcurrent or overtemperature protection on this device. This is one of the more popular plug-and-play home automation products on Amazon. It's dangerous if someone with the right knowledge wants to ruin someone's day. Now, the likelihood of being attacked this way is probably pretty slim, but why allow it at all? This brings me to my point. While I don't think we need light switches in the modern home, I also don't think handing control of our devices over to cloud services or even really relying on internet connectivity at all times is a good idea, for whatever reason you like. This is a Raspberry Pi connected to a relay board through its GPIO or general purpose input-output port. There is some Python code running on it that reads this temperature and humidity sensor and uses that information to determine when to flip the relays on to control the heating and cooling system. I'll be doing a video specifically on this device and building smart thermostats, but the reason I'm showing you this now is because it contains all the components necessary to make one of these plugs, and for about the same price, give or take. This specific example would actually replace 8 of these plugs for twice the price of this one, with a little extra assembly. I will be doing videos on how to build exact replacements for various products over the next few months, but for now I wanted to explain the reasons you should consider building many of these devices yourself, provided you understand enough to safely do so. This is usually as easy as following some pretty simple guidelines and instructions, but I will talk about when to DIY and when not to in those videos as well. Through the course of these videos, I hope to give you inspiration and instruction on building your smart home with peace of mind as well as lower price tags. This approach isn't for everyone, but even those who think they may not know enough to solder a connection, modify home wiring, or write some code might find themselves more capable than they realize. I'd like to see everyone benefit from creating the smart home they want, rather than the one everyone wants to sell them. Even the man who created these amazing devices underestimated their usefulness, but now there is no limit to what you can make out of them. Just make sure you're in control of your devices. I do hope you enjoyed the video, and of course, if you did enjoy it and haven't already done so, please do subscribe to the channel. If you want to know what's going on between episodes, you can follow Smarter Circuits on Twitter @CircuitsSmarter, and if you'd like to help make more and better videos possible, consider becoming a patron on our Patreon page linked below. Thanks for listening to me ramble, and I do hope you'll join me for future videos as I continue building smarter circuits.